Hello and welcome to the Chemistry Clinic brought to you by Boost Revision. This is a Year 12 revision class, which is going to be all about general organic chemistry. So as far as I know, most of you will have just started organic chemistry, or perhaps will be starting it in the next couple of weeks, or have just recently done it. So many of you will have spent the first few months of AS doing atomic structure and calculations, and now you're kind of getting into the more meaty organic chemistry, which will hopefully start to enable you to link between different topics in chemistry. So some of you will have done some organic chemistry before at GCSE. So the first section will be a bit of a reminder of some key definitions and how to draw different types of formula. But we'll very quickly get into some the newer A-level stuff, such as drawing skeletal formula and the IUPAC naming rules. So the first half of the session, we're going to go over some key terminology, the key functional groups, how to draw the different types of formula, and how to name compounds. And then towards the end of the session, we're going to go over some practice exam questions so that you can practice how to actually put these things into practice. Just a note for at this stage, that most of the exam questions actually do ask for much more detail than we'll be covering in this session today. So this is really an introductory session just to get your head back into the idea of thinking about organic molecules, naming them, figuring out what they are from their formulae or their structures. So without further ado, I'm going to share my iPad screen with you. Okay, there it is. You should hopefully be able to see that now. Right, so yeah, we've got some key definitions here that you'll need to know and remember throughout your organic chemistry studies. The molecular formula you will have come across before. This is the number of atoms of each element in a molecule. So this is the actual number of atoms of each element in a molecule. Sometimes you may actually see a definition say the actual number, but I think, for most intents and purposes, that's actually implicit. So the molecular formula tells us the actual number of atoms of each element in a molecule. The empirical formula is the simplest whole number ratio of atoms of each element in a compound. It could be a molecule or it could be an ionic compound, which is why we say compound. But in a similar way, it's telling us which elements are in that molecule or compound, but what it's not telling us is how many atoms of each element we have in that molecule or compound. So we'll get to some examples to see how these differ in a second. The general formula is something that's commonly used in organic chemistry. And this is an algebraic expression of a formula that describes any member of a homologous series. And this term homologous series is an important one to understand because it's really the key to understanding organic chemistry. A homologous series is a group of compounds or a series of compounds that have the same functional group and the same general formula. So for example, alkanes and alkenes, these are examples of different homologous series which have different functional groups. And within the same series, they have the same general formula. Members of the series have different numbers of carbons, and each successive member differs by CH2. So the first one, for example, for alkanes would be CH4. And then the second one will have an extra CH2 attached to that. So that would be C2H6. So again, we'll see some examples of alkanes in a second. But another thing to remember about homologous series is that all members of a homologous series will have the same chemical properties, which means that they'll do the same reactions. If one reacts with water, the other will react with water. If one reacts with an alcohol, the other will react with an alcohol. So that's what's meant by chemical properties. And all members of a homologous series have the same chemical properties. They also show a trend in physical properties. Oops, that's meant to be a highlighter, sorry about that. So yeah, they also show a trend in physical properties. So physical properties are usually things like melting point, density, and things like that. So if you're looking, for example, at the series of alkanes, you'll see that as the alkanes grow larger with a longer carbon chain, the physical properties will change in a regular pattern. So that's what we call a trend. So for example, with alkanes, you can say that the more carbons, the higher the boiling and melting points. So this is a trend in physical properties, and all homologous series will be similar in that way. They'll have the same chemical properties, they'll do the same reactions, and then they'll show a trend in physical properties. So before we go ahead and look at some of the specific functional groups, I just want to kind of highlight how you can use the specification to help you in your revision. Some of you will be having exams in January, perhaps mocks coming up, and revising is really much more about just reviewing what you learned in the lesson. It really starts with making sure you understand what you need to know, and then figuring out for yourself how much of that you do know and what you still need to learn, as well as finding out what your strengths and weaknesses are within the subject. So I'm just going to flip to a different screen where we can see the specification, and you can download this from the website of this is OCRA. You can also download this from our website, boostrevision.com, as well as lots of the past paper exam questions that you might want to have a go at. So this is module 4, core organic chemistry, and you can see here that in this module we're going to look at nomenclature, which means naming, and formula representation, functional groups, which are the different homologous series with the different functional groups, organic reactions, and isomerism. We probably won't get time to go through isomerism today, but you may have remembered this from GCSE, which is when you have the same molecular formula but a different structural formula, so the atoms are arranged in a different way. And we'll have a lesson on isomerism probably later on. Aliphatic hydrocarbons, these are straight chain hydrocarbons. Aliphatic is just a name for straight chain hydrocarbons, whereas aromatic would be for hydrocarbons which have a benzene ring. Alcohols and haloalkanes, practical skills, and organic synthesis. So organic synthesis just means making organic compounds, and one of the things you'll need to learn about, as well as the different functional groups and how to draw them, is what reactions these different compounds do and what is needed in terms of heat or catalysts and things like that to make these reactions happen. Instrumental analytic techniques to provide evidence of structural features in molecules. So this is things like infrared spectroscopy, mass spectrometry, and later on nuclear magnetic resonance spectroscopy as well. So for now we're just going to go over the basics, but I just wanted to highlight how important it is to use the specification and how it can really help you to structure your revision and help you to understand what you do and don't know yet. So in the basic concepts topic here, we're going to be going over some of the key things here, like the IUPAC rules for nomenclature, which means naming, systematically naming organic compounds. We'll look at general formulae, structural formulae, and displayed formulae, as well as skeletal formulae. And again, just highlighting the fact that even if you don't have your own exhaustive set of notes for things like definitions, the specification has them all there. You know, if you're not sure what a general formula is, you can come to the specification and you can actually see this is the definition the examiners are expecting you to write in the exam. So if you're in doubt, you don't have your textbook, you're not sure which website to trust, always go back to the specification to really help you to identify what it is that you need to know, and things like definitions are clearly laid out there. Okay, so kind of linking on with this idea of looking at these different types of formula, we're going to go back to the other screen and have a look at different functional groups and how these different formula work for these different functional groups. So we'll take an example here of alkanes. Okay, so alkanes are the simplest functional group. And that's because they are known as saturated hydrocarbons. So saturated means that they have the maximum number of hydrogens for every carbon. Every single carbon has a single carbon-carbon double bond, which is why we can say that we have the functional group is just the CC with a single double bond. And its general formula, you may remember from GCSE, is CN H2N plus 2, which means for every one carbon there's going to be, if one is N, then 2N plus 2, 2N would be 2 plus 2 is 4. So that gives an example of CH4 would be methane. Okay, so now looking at the molecular and empirical formula for for this functional group or for this homologous series, we're going to use the example of butane. Okay, so butane is the alkane which has 4 carbons in its chain. So we have the molecular formula will be C4H10, and just double check that that matches with the general formula. So C4, N is 4, 2N plus 2 is 10. So that's the molecular formula for butane. The empirical formula, you'll remember from the first page, is the simplest whole number ratio of atoms in the element. So in order to make this into an empirical formula, we just try and find the simplest whole number ratio between 4 and 10. So 4 doesn't go into 10, but 2 goes into both of them. So if we divide both numbers by 2, we get C2H5. And that will be the empirical formula for butane. The displayed formula for butane, a displayed formula, as we saw in the specification definitions, has to show every single atom in the molecule and every single bond. Okay, so we're going to draw this butane molecule here, and it's going to be 1, 2, 3, 4 carbons all in a chain, and then the 10 hydrogens are attached all the way around the outside. So 2 on each of the carbons in the middle, and then you've got the extra hydrogen on the end 2 carbons, and that's where the +2 comes from. So we've got a chain of 4 carbons in a row with the 10 hydrogens around the outside. So make sure for displayed formula that you're always showing every single atom and every single bond. The structural formula, again, you'll be able to refer to your specification for this. This is a formula that slightly simplifies the displayed formula by focusing on each carbon and how many hydrogens that carbon has. So I quite like to draw the displayed formula before the structural formula, even if I'm trying to draw a structural formula, because it really helps me to identify which carbons have which hydrogens attached. So the structural formula for this particular example would be CH3, because this first one has 3 hydrogens on it, then CH2, CH2, CH3. So a structural formula is written in one line, showing each of the carbons in the chain and how many hydrogens are attached to it. It gets a little bit more complicated later on, like for example when we have branching, but I'll show you how you deal with that later. A skeletal formula is new for A-level, and the skeletal formula doesn't show the names of either the carbons or hydrogens, but it will show the symbols for anything else, like if there's an oxygen attached or an OH group or a Cl. But the assumption in a skeletal formula is you're going to have carbons and hydrogens, so we're just going to use the idea of a backbone to represent that carbon chain, and we're just highlighting any other functional groups that come along by adding those in. So I'll just remove this for now so it's a bit clearer. So the skeletal formula for the same example will show the carbons as the ends of lines or corners. So in this case, we've got 1, 2, 3, 4 carbons. So this end of the line, this corner, and this end of the line, each represent a carbon. And if there's nothing else attached to it, like oxygens or chlorines, for example, then we can assume that that means that the carbons are all surrounded by hydrogens, okay? We'll look at how this works with double bonds and other functional groups in a second, but the key thing to remember for a skeletal formula is it shows a backbone of your carbon chain at an angle, with each corner of the angle representing a carbon. Okay, so let's do something similar with the next functional group, alkenes. Feel free to have a go yourself before you watch me do it, because that can be much better practice to see if you know this kind of stuff already rather than just watching someone doing it. Okay, so we're going to, first of all, remind ourselves of the functional group. So in alkenes, the functional group is a C double bond, a C double bonded with a C, a carbon-carbon double bond. We call alkenes unsaturated because it is possible to add more hydrogens onto that carbon chain by breaking the double bond. And that double bond is its functional group because that's kind of what we call like this sort of the active area of the molecule. So if an alkene is going to react, it's usually going to react from that carbon-carbon double bond, and that's why we call it the functional group. Its general formula is CnH2n. So that's because the carbon-carbon double bond means we can't have as many hydrogens as we would have had with the similar alkane molecule. So we're going to do the same thing as we did with alkenes now for the example of butene. And we'll come on a little bit later to understand why we have the 2 number in the name of butene there. So the molecular formula will be C4H8. So the but tells us we have 4 carbons, and then the 2n is 4 times 2, so that's C4H8. The empirical formula then, 4 does go into 8, so we can just be, the empirical formula will just be CH2, because that's the simplest whole number ratio of C4H8. The displayed formula, 1, 2, 3, 4 carbons with a double bond in between the second and the third carbon, and that's because of this naming here. This naming with the 2-ene tells us that the functional group, the alkene functional group, starts at the carbon number 2. So we know that this must be in the central area there between carbon 2 and carbon 3. And then we can just surround the rest of the molecule with hydrogens. And just be careful here, it's quite common to accidentally just put extra 2 hydrogens at the bottom here, but that's not correct because it wouldn't give us the right formula. So just be careful. Just be careful as you draw your displayed formula to make sure you've got all of the carbons, all of the hydrogens, and not too many. The structural formula then will be CH3, CH, CH, CH3. So hopefully you can see as we go along these different carbons here, that's the CH3, that's the CH, that's the other CH, and that's the CH3. The skeletal formula then will again be 3 lines connected like that, so the 4 ends showing the carbons. But now because we have the double bond, we draw another line parallel to that. So that represents the double bond, okay? Next is alcohols. So alcohols, the functional group is OH, so I've shown this OH over here, okay? And the R just represents any carbon chain. So depending on what the context of the question is, you wouldn't necessarily be expected to show the R, but strictly you should show the R to show that this OH is attached to a carbon chain. So R represents a carbon chain. The general formula will be CnH2n plus 1 OH, showing that we have, for every carbon, we have 2n plus 1 hydrogens and then the O and the H. Sometimes you might see this written as CnH2n plus 2 O, and both would be correct. But generally this one is preferred because we can then see that functional group at the end of the general formula. So let's have a look at doing these example molecular and empirical and displayed formulas. So the molecular formula would be C4H7OH. And actually this is an interesting example where strictly the molecular formula should be written with each of the atoms in order. So actually the molecular formula should follow this general formula, C4H8O. This is because the molecular formula is not supposed to show the structure of the molecule. It's just supposed to show the number of each of types of atoms in the molecule. So actually the molecular formula should normally be this one here, even though this would be accepted as a general formula. Okay, so that's maybe a little confusing, but the key thing is that in the general formula, we're trying to identify the fact that an OH is there. In the molecular formula, we're just interested in how many atoms of each element you have. Okay, then the empirical formula would actually be the same, C4H8O, because we only have 1 oxygen, so we can't divide the other numbers by anything to get anything that's simpler, a simpler ratio. This is the simplest ratio already. The displayed formula then will be similar to what we had for the alkane, but instead of the H at the end, we have an OH. And I did say that we need to show every single bond, so it would be best to show the O and the H with a bond in between, even though sometimes you'd see it as an OH, and some examiners would accept it, again, depending on the context of the question. But in general, to be safe, I would always show this bond between the OH if you're specifically asked to draw a displayed formula. The structural formula is going to be CH3, CH2, CH2, CH2OH. Okay, and again, hopefully you can see how I'm focusing on each C one at a time to get that structural formula. Then the skeletal formula, again, will look similar to the others, but now we can show we have an OH at the end. So this is where some people get a little bit confused. These, I'll draw them in a different color. These corners here are our carbons. But because we have something attached to this last carbon, we do have to draw this extra stick and show that the OH is attached to it. But that doesn't mean that there's another carbon on the end of that stick. So try to be clear that if you have something attached, you will show a stick to show that bond. But that doesn't mean, that means that in this case, it's the oxygen that is attached to that bond. There's no extra carbon on the end there. So we still have the same 4 carbons in that same structure as we had with butene and butane, but now we have the OH group attached on the end. Okay, same thing for carboxylic acids. These should all be functional groups that you came across at GCSE, so hopefully they'll be familiar to you. The functional group for carboxylic acid we've got up here, which is the C double bond OH. And that gives us a general formula of CnH2nO2. Let's stick with a trend of what we were doing before of showing a butanoic acid in this case. So I'll write that down, e.g. butanoic acid. Okay, so the molecular formula will be C4H8O2. The empirical formula, we can divide the two through. So we've got C2H4O would be the empirical formula of this carboxylic acid. And then the displayed formula, 4 carbons in a row. At the last carbon, we've got the functional group. And then we have the H's surrounding all of the rest of the carbons. And just double check that this makes sense with the molecular formula. So we have 4 carbons, we have 7 H's around the carbons in the chain, and the other H attached to the OH, so that's 8. And then we have the 2 oxygens. So we've got C4H8O2. Okay, so just double check things like that sometimes as you're drawing, especially if you're still getting used to the idea of these things. The structural formula then would be CH3, CH2, CH2, COOH, and that's how we draw the functional group for a carboxylic acid in the structural formula format. And I think I just move this up a little bit to give a bit of space for our skeletal formula. And the skeletal formula will be, again, that same thing for butane, and then we add the double bond OH. So we can add OH here and the double bond O there. So again, we don't have to write the carbons, but it is important that we only draw the right number of carbons in that skeleton. So we don't draw these dots on in the exam, we just draw what we just draw, but just to show you how to identify this, we've got the first carbon here, the second carbon here, the third carbon here, the fourth carbon here, and then that's your double bond, OOH. Okay. I may not go through these other ones in a huge amount of detail, but I will put the worksheet up onto the website so you can have a go at this for yourself, and please feel free to ask any questions if you're not sure. But yes, we've got the ester functional group, which is made from reacting an alcohol with a carboxylic acid, usually. I'll let you work out the general formula and etc. The displayed formula, if let's take an example of, let's say, ethyl ethanoate. Okay, and I'll draw the displayed formula for this, and you can maybe fill out the rest in your own time. So ethyl ethanoate, you're going to have the ethyl group here attached to the O on the left, making sure you've got all of your hydrogen showing. So eth means 2 carbons, and that's actually the part of the molecule that comes from the alcohol. Then we have the ethanoate, so then it's attached to the C double bond O. This part came from the carboxylic acid, so it was an ethanoic acid making ethanoate. So we have, if it was ethanoic acid, we have these 2 carbons here. And again, just in general, when writing displayed formulae, just try to make sure that you've got the right number of bonds on each of the atoms. So every carbon should have 4 bonds. And sometimes it might be tempting to put an H down at the bottom here, but that's wrong because each carbon can only have 4 bonds. This one has 1 bond here, 2 bonds there, and 1 bond there. So it's already got its 4 bonds. So just be careful about adding extra bonds that shouldn't exist. Each oxygen only has 2 bonds. So again, we've got the 2 bonds here. We've got this oxygen with these 2 bonds. Just have some ways of common sense checking your molecules to make sure they make sense. The skeletal formula for this one might be a bit weird. So we've got that's our 2 carbons on the left hand side. Then it's attached to an O. So we have an O like that. Then it's attached to a carbon, which is attached to a double bond O. And then it's attached to another carbon. Okay, so this is what the skeletal formula would look like for this ester. This being this carbon here, this being this carbon, then this is this carbon, and this is this carbon. Okay, so hopefully that makes a bit of sense, and hopefully we're skipping over the things that are a bit repetitive but showing you the important aspects of the different functional groups. Okay, so this is our esters. Another couple of functional groups that are newer at A level are aldehydes and ketones. So here again we've shown the functional group. I'll let you work out the general formula, molecular formula, empirical formula, and I'll just show a displayed formula again. Example, butanol. So aldehydes always have this AL naming at the end, and this functional group is always at the end of the chain. So butanol would be 4 carbons in a row with this double bond O and this H here, showing all of the bonds, all of the H's. This butanol would be C4H8O. I'll just move this out of the way a little bit. Okay, so we can see that's its molecular formula. Empirical formula would be the same as the molecular formula because we can't divide that O into anything. And then the structural formula, again, just be careful of how you're showing the chain, not to show too many carbons, but making sure to show that O at the end. So you're going to have 1, 2, 3, 4 carbons, the double bond O at the end here. It is quite important that we have the double bond O coming off at an angle. It doesn't matter if you're going to draw it It doesn't matter which way you draw it, so whether you go up first or down first, these are both the same molecule, but it is important that you show the corners because the corners represent the carbons. Okay, so just a note as well about the structural formula here. This bit at the end, so we've got the CH3, CH2, CH2, and then CHO. It's really important with aldehydes that you show it as CHO as opposed to COH, because then that will be ambiguous as to whether a COH would be the alcohol or the aldehyde. So COH would be for the alcohol and CHO would be for the aldehyde. So it's really important for this, for aldehydes, to always show that functional group at the end there as CHO. I'm just going to move this so you can kind of see. Oh. So you can see how this structural formula kind of relates to the displayed formula. Again, each carbon being represented in order down here. Okay, then a ketone is similar to aldehydes in that it's got a double bond O attached to a carbon, but this time the double bond O is not at the end of the chain, and that makes ketones different to aldehydes. It makes them do different reactions, and you'll learn more about that later on. But it's really important that if the double bond O is at the end, that's an aldehyde, and if the double bond O is in the middle, that's a ketone. Okay, but they do have the same general formula, I believe. We'll draw an example here of butanone. And actually in this case, we'll talk about this with naming, we would normally see a number here to tell us which carbon the double bond O group is on. So we'll call it butan 2-one, because it would be possible for that double bond O to be on the third carbon, but not on the last carbon. So let's have a look here at the displayed formula. C, 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 C. If it's butan 2-one, then the second carbon has the oxygen attached, and then we have everything else being hydrogens. So in this case, if we compare this to the general formula, this is this R group, and this is this R group. Well, I'll show it maybe in a different color. So this is this R group here. Okay, so as we said earlier, an R group is just a carbon chain, which will be made up of carbons and hydrogens. So when we're drawing the functional group, we can assume that that is attached to any carbon chain. And in ketones, that carbon chain could be either the same either side, or it could be different either side. So the key bit is the functional group of the double bond O that's in the middle of the compound. And again, we'll go into more detail about this with naming later on, but just sort of again referring to the fact that in butan 2-one, this name shows that we have the one, the ketone group, is on the second carbon here. If it was on this group here, we might think to call it butan 3-one, but actually that would be the same molecule. That would just be a rotated version of the same molecule. So actually we can't actually have butan 3-one. If we wanted to put the double bond O at the end instead, for example, on this last carbon, then that would actually make it into an aldehyde and not a ketone. And the same thing over here. So in actual fact, when I was doing the naming earlier, we can write the butan 2-one to make it clear that it's on the second carbon, but because if it was on the third carbon, or first or fourth, it's not a ketone anymore. Sorry, the first or fourth is not a ketone, it's an aldehyde. If it was on the third, it would be the same as the 2. We actually don't need this 2 here. We can just rub that out and call it butanone. Okay. So the numbering, we'll look at the IUPAC naming rules in a second. The numbering is really important to make sure that your naming of your organic compounds is very specific, and that from the name of the compound you can identify which organic compound you have. So we have to include numbers to avoid any ambiguity. And in general, the longer the molecule, the more we might have to put numbers in, because there'll be more different orders that we can have these functional groups attached in. Okay, so we're going to go on to the naming rules now, and actually to start off with, I'm going to share a different screen with you, so bear with me while I do that. So here are the key rules for naming naming organic compounds. Okay. So the first step is to identify the longest continuous carbon chain containing your functional group, and this gives you the stem part of your name. So with alkanes, for example, this is where you get the bute, etc. The main functional group usually gives the ending. So again, with alkanes, that gives us an ending of ANE, or with alkenes, it gives us an ending of ENE. So the longest continuous carbon chain gives us the stem of the name, and then the main functional group gives us the ending of the name, usually, but sometimes will give us the beginning. We'll talk about that later. The number, you number the principal chain from one end to give the lowest numbers. And so this is what I was talking about with the ketone a few minutes ago, is we always want to have the smallest numbers in the name. So butane 2-one is actually the same molecule as butane 3-one, and because 3 is obviously a higher number than 2, we always prefer to use the 2. So you can number your carbons from the left to right or right to left, but the aim is to give the lowest numbers in the name. If there's more than one longest chain, you choose the one with the most chains, side chains or groups, and you usually need to focus on the chain that has the main functional group attached. Okay, so if one of the chains is just a carbon chain, but the other chain has, for example, an OH on it, then you'd focus on the chain that has the OH on it. The names of the side chains appear in alphabetical order. Okay, so we have side chains that could be methyl or ethyl or butyl, etc. These are carbon-based side chains. But if we have more than one of them, we have to put them in alphabetical order. So even though, for example, methyl has 1 and ethyl has 2 carbons, you might want to put them in that order. You actually need to put them in alphabetical order of the name. So in this case, butyl, ethyl, methyl, propyl, even though that's not the numbering order. Each side chain is given its own number. So if you have 2 side chains on the same carbon, they both get the same number, but it's said twice. And again, we'll look at examples of this in a second. So if you have 2 methyl groups on carbon 2, that would be 2,2-methyl, whatever it is. If identical side chains appear more than once, then you prefix it with di, tri, tetra, penta, hexa, etc. So this means, again, like I was saying a second ago, if you have 2 methyl groups on carbon 2, you'd have the 2,2 to show they're both on carbon 2. And then instead of just saying methyl, you'd say dimethyl to make it really clear that there are 2 methyl groups on that carbon. So it would be 2,2-dimethyl, and that would show you that you have 2 methyl groups both attached to the second carbon. Numbers are separated from names by a hyphen, e.g. 2-methyl-heptane. So whenever you have numbers in the name, it could be at the beginning of the name or in the middle of the name, you always separate the numbers from the names or the words with hyphens. Numbers are separated from other numbers by commas. So for example, it's quite common to have multiple numbers at the beginning of your name. So it would be 2,3-dimethylbutane. That tells us that there are 2 methyl groups, and one of them is on carbon 2 and one of them is on carbon 3. So those are the main rules that you need to know about. And now we've got the stems and prefixes and suffixes to remember. So again, we've got the alkanes, which are ane, alkenes, ene, alcohols, etc. I'll have this put up on the website so you can refer to it easily, but you can see that each functional group has its own prefix or suffix or stem that you use to name that specific thing. So for example, with aldehydes, as we mentioned before, if it has an al at the end, that tells us that this is an aldehyde, and therefore we're going to see that C double bond OH at the end, so the CHO group at the end. One thing we haven't mentioned yet are alkyl groups. So this is where you have an R group or a carbon-based chain as a branch off another chain. And we also didn't mention halogenoalkanes. So here we have chloro, bromo, iodo. So the start of it comes from the name of the halogen. So chlorine, for example, but then instead of chlorine, we say chloro, and then that's attached to, for example, chloromethane or chlorobutane. So that's the stems that you get for your functional groups. So as we said, the functional groups give us the stem, and the number of carbons give us the number in the stem. So for example, 1 carbon is meth, 2 carbons eth. So you need to know all the way up to 10 carbons. So it could be, for example, pentane or hexanol, or octanol, or it could be nonyl, which is an alkyl group with 9 carbons, and then something else that's a longer chain, so perhaps nonyl decane. So you need to remember the naming for numbers of carbons in the stem that go from 1 to 10, and then the prefixes and suffixes, which are for our to show our functional groups, which either come at the end or the beginning of the name. So the number of carbons gives us the stem, and the functional groups give us the prefix or suffix. So we're going to go to some examples now. So if you're following on, then do have a go first of all at drawing these 3 examples here: ethanol, ethyl butanoate, and chloroethane, before I go through how to do it. And then we'll also have a go at naming some from the other way around. So I'll give you the drawing, and then you have to give me the name. So I'm going to go back to my iPad for a sec, but in the meantime, do please have a go at that for yourself so you can test if you would know how to do that. Okay, so how to draw ethanol. We were talking about this earlier. Ethanol's a relatively easy, an easy one to do because it's not got any numbers or any weird branching or anything like that. So usually for drawing, we can do skeletal formula, or we can obviously do the whole displayed formula showing all of the carbons and all of the bonds in that functional group. We'll use a different color for the next one. Ethyl butanoate. This is going to be an ester that has an ethyl group on one side and then the butanoate group on the other side. So ethyl is going to be CC. And then you've got the ester group here. And this is butan. So we've got 4 carbons in a row surrounded by hydrogens. So once you get the hang of doing skeletal formula, it is much easier to do these, answer these as skeletal formula because you've got less hydrogens to repetitively draw. Just make sure that you're drawing the skeletal formula correctly. So again, like before, we had the 2 carbons and then the O, then the next carbon and then the double bond O, and then 1, 2, 3 more carbons. So 1, 2, 3, 4 for the butan, and then 1, 2 for the ethyl. And again, just try and remove those dots because that's not actually part of the skeletal formula. It's just trying to help you to identify how many carbons there are. So if once you're used to the skeletal formula, that's normally the most kind of efficient way to answer these questions. But sometimes if you're not that confident, it can lead to more errors. So if you're not that confident, I would say stick to displayed formulae. The next one then will be chloroethane. I'll draw that down here. So eth tells us we've got 2 carbons in the chain. Chloro tells us we've got a chlorine. And then the rest is H's because the rest is ethane. So we could have the chlorine anywhere around these on any of the 2 carbons because no matter where we put them, it would actually be the same molecule. So try and think about that as well as you're drawing these things, because sometimes people get confused about when they're drawing, for example, isomers and things, and they start to think that, for example, this molecule is different from the one we just drew here. These are actually the same molecule because these compounds can rotate to become basically the same thing. So, and this is just kind of trying to show you how this is actually the same molecule, just rotated. So just be really careful with that. Same thing with alkenes. These single bonds can rotate, which means that it doesn't matter which carbon you have your functional group on, because all the bonds can rotate, then in 3D space, it's actually the same molecule. What's different is if we had a double bond, carbon-carbon double bond, because that wouldn't allow the carbons to rotate, and that's how you get something called stereoisomers, which you may or may not have come across yet. So let's now look at, rather than drawing from the names, let's look at naming from the drawings. So we've got some drawings here already made up. Have a look at each one and think about how you might be able to name those compounds. So this first one here, we've got 1, 2, 3 carbons, so that's going to have a stem of prop. It's got this double bond, so that's going to be an ene, and this ene is between carbon 1 and carbon 2 because we want to number them so that the carbons, that we have the lowest numbers. But in this case, if we had the double bond over here, we would just change the numbering from 1 to 3, from backwards to forwards, or from left to right to left. And so actually both ways you'd have the same name. Therefore in propene, you don't need the number because it's not ambiguous if you don't put the number in. So we just write propene. Hopefully that makes sense. If you can draw the same molecule but in a different form, like in a different rotation, then you don't need to write the number to clarify. The longer the molecule, the more likely you need to write the number. So just as an example, actually, if I move, I'm not sure how I can do this. Yeah. If we were to draw butene, I'll just move it across here. If we wanted to draw butene, we do need the number to know which of the carbons that butene is going to be attached to, because if we have the carbon-carbon double bond in the first 2 carbons, so we'd number these. Actually, I'll just do skeletal formula again, just to make it a little bit clearer, hopefully. So we've got butene. We could have it with the first carbon. We could have it on the second carbon. But we couldn't then have it on the third carbon because that's going to be the same. These two are the same as each other. Okay, so but we do need the number to know whether it's going to be this one, which is going to be but1ene, because that's the first carbon. 1, 2, 3, 4 is how we would name them. And here we would name 1, 2, 3, 4. So this would be but2ene. So we'd have to make sure that we'd write the number inside the molecule here. So I'll write it here. but1ene, and then but2ene. Okay, so the longer the molecule, generally the more likely you'd have to write the double bond in, or write the number for where that functional group is. But in the case of propene, which was our example, we wouldn't have to write the number in there. This next one, have a look. We've got 1, 2, 3, 4, 5, 6, 7 carbons, but we're not going to say that the number is 7. We're going to say the number is 1. And actually, in this case, our functional group is this aldehyde group here, which is always going to be on the end. So actually, we never have numbers for aldehydes because we always just assume that's on carbon number 1. So this is just going to be, oh, I've lost my color. Yeah, this is just going to be hept for the 7 carbons in a row, and now for the aldehyde group. And then this last one down here, we've got 1, 2, 3 carbons in the straight chain, and then this is a carbon coming off it. So this would be our methyl group. We can't, just another note about isomers and things like that, we can't have the methyl group on this carbon or this carbon, because if we did, then we would have, that would just be a longer chain. So I'll just draw that out to kind of show you. If we have the CH3 here and the rest of the molecule is the same, then this is actually going to be just butane, because that methyl group isn't actually a branch off the carbon. So again, in this case, you can't have the branch on the first carbon or the second carbon. So it's not ambiguous to have, you don't need a number in there because that methyl group will always be on that central carbon. So I'll erase this bit for now. And yeah, so the methyl, we have the methyl in the middle of that, and we've got the rest, the long chain is 3 carbons long. So it's going to be methyl propane. So prop for the 3 carbons in a row, ane because it's all single bonds, and then methyl because that's the CH3 attached as a branch to the main chain. Okay, so I think we've pretty much gone over all the basics, and we've got about 10 minutes left to go through some exam questions. So we'll just get to that straight away, so you've got some idea of how to actually apply this stuff to exam questions. So I've highlighted the questions here that we're interested in. As I said before, a lot of the questions will be asking more complex stuff than we're ready to do at this stage. So we're just going to focus on some of the naming questions and some of the questions we can answer from what we've done so far. So here we go. We've got some information about 2 reactions of compound C, and it given us a compound D that it's now asking us to name. So it wants us to give us the systematic name for compound D. So again, we can see if we look, we've got 2 carbons in the main carbon chain. So that's going to be an ethane of some sort. But then we have 2 chlorines, and they're both on this right-hand carbon. And then we have 2 bromines, and that's on each of the other carbons. Okay, so we want to name the carbons so that we have the smallest numbers. So we're going to name from this side, that's 1 and that's 2. So we're going to have the groups in alphabetical order. So we have 2 bromines, so that's going to be dibromo. And then we have 2 chlorines, so that's going to be dichloro. And then our 2 C's is our ethane. And then we have to write the numbering to make it really clear which of those carbons the chlorine and bromine is attached to. So the bromine is, we've got 1 bromine on 1 and 1 on 2. So we're going to do 1, 2 hyphen dibromo. And then we're going to have 1, 1 dichloro and then ethane. Okay, so making it clear with the numbers that we have. So every side group has its own number. We separate the numbers with commas, and we separate the numbers from the letters with hyphens. If we have more than one side group, we say di, methyl, or dibromo, or dichloro. In this case, we have 2 bromos and 2 chloros. We have to put the bromine, bromo and chloro in order, an alphabetical order to match with the systematic rules. And so that gives us our systematic name for this compound D. The next one, give the systematic name for alcohol C. So we've been given a structure for the alcohol, and we want to give the systematic name for that structure. So we have to identify how many carbons. So we've got 1, 2, 3, 4 carbons in the longest chain. This is our alcohol group. And then this is a methyl group. So again, with a skeletal formula, all of the ends of sticks or corners are carbons, apart from where it's actually attached to an OH. So we're going to number these from right to left because we want the number attached to the alcohol to be the smallest. So we'll do 1, 2, 3, 4, and that means it's going to be 1, 2, 3, 4 is butane. Going to be butane something, but for the 4 carbons, and then it's butane 2-ol because that alcohol group is on the 2nd carbon, and then we need to identify this methyl as well. So the methyl is on the 3rd carbon, so we say it's 3-methyl butane 2-ol. Okay, so again, this is a situation where you might want to write 2-methyl butane 3-ol, but we want the numbers to be as low as possible, and when we focus first on the number on the chain that has the functional groups. In this case, it's the alcohol group. Okay, propanoic acid is a member of the homologous series of carboxylic acids. Suggests the general formula for carboxylic acids. So if you don't remember it, you can just look at the propanoic acid and work out what the algebraic formula is. So for example, we've got 3 carbons, so that's C3, 3 plus 2 plus 1 hydrogens, that's H6, and then we've got 2 O's, so that's O2. So if we put that into the algebraic formula, that's going to be CN H2N O2, and that's your general formula for your carboxylic acid. This is more of a question about isomers, so actually we're going to skip that for now. We're just going to finish with this one, which is maybe a bit of a kind of out of the ballpark thing, because we haven't really looked at this kind of structure yet, but it's nice to get into the idea of recognizing different structures based on the structural formulae. So again, we just want the molecular formula for this naphthalene. So we want to count how many carbons there are in this. So remember, each carbon is a corner here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the molecular formula is going to be something which involves C10. Okay, so we have to work out how many H's there are. And if you think about how many double bonds there are, we can only have one H on each of these points here. We can't have an H here because we've already got 4 carbons, and we can't have on here because we've already got 4 carbon bonds. So we can have here as well. So that's 4 on one side and 4 on the other side. That's 8 hydrogens. That means this is going to be, the answer for that's going to be A. Okay, so I think we've gone over most of the basics that we need to go over for now. Hopefully this has been a good kind of reinforcing of whatever you've learnt in class, covering the key functional groups, the different types of formula, what the naming rules are, and how to apply those naming rules to different types of examples in the exam questions. So good luck with the rest of your revision. Remember that we're going to have a session like this every week, and you can check on the website what the sessions are going to be, what the topics are going to be each week. Over the next few weeks, we're going to be going back over some of the stuff that you would have learnt in your first term to help you to prepare for the exams that you've got coming up in January. But hopefully you enjoyed this organic revision topic as well. Please send us an email, or send me an email, ligai@boostrevision.com, if you've got any feedback, or you can leave comments in the website area. And thank you very much for joining. I really hope this helps, and hope to see you again next time.